Alright guys, so we got a couple of videos to wrap up 3.8 and the goals remain the same. The goals of this video is to look into the derivatives of inverse trig functions, and specifically today we're going to look into arctangent and arcsecant. So in the last video, we dove into an example of find the derivative of arcsine, and we kind of proved the exact way as how to get to what the formula, quote unquote, was for the derivative of arcsine or sine inverse. For this example and the purpose of today, I have already provided you the formulas for find the derivative of tangent inverse and secant inverse to save a little bit of time. If you want to look deeper into where these come from, check out your books, guys, and see exactly where in 3.8 where the derivatives are, I guess, proven or derived from, and where we get these formulas in this case. And so for our goals today, we are going to look into an example of find the derivative of secant. Okay, so first and foremost, let's look right on in. If we want to find dx, the derivative of y equals secant inverse of 5x to the fourth. Okay, so now be careful, this is not 5x to the fourth times secant inverse. This is secant inverse of the function 5x to the fourth in this example. And so kind of looking at where our sine formula takes us, it's a little bit funky, but kind of how this was derived was when you take that square root, you can kind of see that you get the plus and the minus side of things. And so that's kind of where we get the absolute value of in this formula. But again, not overly for our purposes, too much for today. So we're just going to kind of utilize the formula to our advantage. So secant inverse of 5x to the fourth. So let's just take a look and substitute what our u is. Well, our u in this example is going to be 5x to the fourth. So wherever I see u in our formula, I need to replace it with 5x to the fourth. So if I want to find dx, this is going to be 1 over, we have the absolute value of u, which is the absolute value of 5x to the fourth, multiplied by the square root of, in this case, we're looking at u squared minus 1. So really that's 5x to the fourth quantity squared. And then minus 1. All being multiplied by the derivative of u. That's where our du dx comes into play. So multiplied by the derivative of u. So the derivative of the inside function is 4 times 5, which is 20, and 20x to the third with our power rule being used right there. So now let's take a look. Kind of just taking this down and simplifying it a little bit more, we get 20x cubed over the absolute value of 5x to the fourth. Well, that's positive already, so we can kind of keep it there. 5x to the fourth times the square root. 5x to the fourth quantity squared is 25x to the eighth minus 1. And then the only thing to really do is just kind of simplify. We have x cubed, and we have 4 down there. We have 1, 5, and then we have 4 up top. So we have 4 over, in this case, will be x times 25x to the 8th minus 1. And this is derivative in respects to x. So there's a little bit of an example as to how we can use it in terms of secant and I guess kind of tangent as well too, because it's literally just using the formula as we look into those. So a couple of ones that I highly suggest kind of finding out on your own to give it a shot is first and foremost, let's look here at one with tangent. All right, x squared minus 1, so give that one a shot. And then also give a shot with one with secant. And let's look at secant inverse of 1 over t. All right, guys. For this purposes, kind of just what we've been looking at for today, answer for y equals secant inverse, I'll give you guys a go on, and then we'll talk about the tangent inverse first thing on in the morning. But you can kind of check your answers for secant, and you should have seen in this particular example. -1 over square root of 1 minus t squared. All right, so that's what we should have seen for our answer for this one here. Okay, so check your answers on that one, guys. Like I said, we'll go over the y equals tangent inverse first thing, and great job.